The third type of isomer is called a geometric isomer. And geometric isomers are in the stereoisomers category because they have identical bonds to the transition metal center, but they're oriented differently in space. So with the geometric isomers and the optical isomers, it's very, very beneficial for you guys to either use molecular model kits if you have them, or to use some of the online tools that you have out there in order to determine what these complexes are. We briefly touched on cis and trans isomers the other day in class. Cis and trans isomers fall into the geometric isomer category. One of the classic cases of cis-trans isomers is PT NH32 Cl2. This particular complex has a coordination number equal to 4, and it's a square planar complex. If we draw out the cis isomer, it's going to be PT, and the square planar is simply a coordination number of 4 all in the plane of the board. It's going to have NH3s, if they're in the cis configuration, they're going to be on the same side or adjacent vertices. And the chlorides are also going to occupy adjacent vertices. So this is our cis isomer. The trans isomer is going to be platinum in the center, and the NH3s are going to occupy opposite vertices. Same thing with the chlorides. If we look at the properties of this particular molecule, when we look at these properties for this particular case, we're not going to see any differences in color. But if you look at the cis isomer of this particular compound, this has been a successful cancer treating drug. The trans isomer is ineffective at killing cancer cells. So here in this particular case, we don't have any color difference. But when you're looking at biochemistry, when you're looking at drugs and how they could potentially bind to DNA, the cis versus the trans isomer is going to be very, very, very important. So one of the things that I want to also point out, if you have a geometric isomer, we consider those stereoisomers, which means they have identical bonds. If you look at the cis case, we have a platinum, and that platinum is coordinated to 2 NH3s, and it's also coordinated to 2 Cl minuses. If you look at the trans complex, we have platinum at the center, which is coordinated to 2 NH3s and 2 Cl minuses. So everything that's coordinated to that central transition metal is going to be exactly the same. They're just oriented a little bit differently in space. If we're talking about cis and trans isomers, cis and trans isomers are possible for octahedral complexes and square planar complexes, but they're not observed in tetrahedral molecules. And this has to do with how the molecules are oriented in 3 dimensions. If we have a square planar molecule, there's a difference between how these NH3s are coordinated on adjacent vertices in the cis case and opposite vertices in the trans case. if we drew a tetrahedral molecule where I have a metal here at the center and I put 4 ligands around that, let's just say I use 2 different ligands, X and Y. If I put the X's here and the Y's over here, and drawing this shape on a 2-dimensional piece of paper or a 2-dimensional board might look like that if I took this metal right here and then put the X here and the X over here on the other side and made these guys Y's, if we compare these 2 structures right here and we look at them in 3 dimensions and rotate them around, we find that they're the exact same complex. They aren't isomers. For example, this X right here and this X right here, the bond angle that's formed between the metal and these X's is 109.5 degrees. Because remember, in a tetrahedral molecule, you have 4 bonds that are 109.5 degrees apart from each other. If we look at both of these X's right here, this bond angle formed right here is also 109.5 degrees. So all we're doing is just rotating this molecule, and it's actually the exact same thing. It's just rotated differently in space. Whereas if we look at a cis and a trans molecule, in this case the platinum complexes, here we have an ammonia-ammonia bond that's 180 degrees. Whereas with this particular cis complex right here, we form a right angle where we get 90 degrees. So based on how these guys are different in space, and not only is the bond angle going to be different, but the actual dimensions or the distance between each of these ligands is also going to be different. Okay? So if I could shrink myself down and be a little angstrom-sized person, and we could take out a tape measure, we would measure the distances here. These ammonias would be different than these ammonias over here. But the X's that I drew, this distance right here and this distance right here would be exactly the same. And that's through the 3-dimensional geometry of these particular compounds. Okay? I'm going to post some tutorials online so you can go through these things and actually view these guys in 3 dimensions. All right? So make sure you keep in the back of your mind what these 3-dimensional shapes should look like.